Hi everyone, thank you for joining us for HDF5 Application Tuning. I'm Lori Cooper of the HDF group, and my coworker Gerd Heber will be presenting this webinar today. Gerd wanted me to tell you there is extra credit for turning on your cameras. He enjoys seeing the reactions, bewilderment, or whatever you've got there. We're planning a 45-minute talk with plenty of time for questions and answers after. You're all capable of unmuting. If possible, please wait till the end, then unmute and talk. You can also use the chat if you need to. We'll be posting the source code in a GitHub repo. So we'll share the link with you. We'll also share the slides and the recording when we get those done. So with that, I'll turn it over to Gerd.
Thanks, Lori. Yeah, welcome. Thanks for joining us today. My name is Gerd Heber and I work for the HDF group. And today's topic is HDF5 application, and that's a very big topic. The emphasis today is actually beginners offer some practical advice, and also that means it's good to start with a simple problem, although we will see very quickly that what looks like a simple problem has a lot of ramifications and may not be so simple in hindsight, but also for clarity in the sense that we will show some tools that we highly recommend you use in your tuning efforts. And the working of these tools is best illustrated if you simultaneously have not to think about two things, think about a complex problem and sort of coming to terms with how that tool works. It's better to have a problem where you kind of think, yeah, intuitively, I know what this problem is doing, and then it will be much, much clearer to correlate cause and effect between what the application is doing and what you see in the tool. It turns out that at least in my limited experience, there are three tools that I use all the time that get me there most of the time. What you will see in a moment is there is a lot of material here, and that can be overwhelming. And I just recommend to go with the flow, ignore the parts that seem irrelevant to you or unclear, and focus just on sort of the possibilities, in the sense that as a result of this, you might see new things that can go wrong. And if they can go wrong, they will go wrong under certain circumstances. So that's important to keep in mind. And you should definitely, after this, if you like one tool or the other tool or all of them, try them with your own code. That's the best way to become familiar with that. There are two parts to this. Number one is today we will work in a little bit of a sandboxy environment. Part two, we will focus on sort of the parallel issues and work on a real cluster. I think the most important message to take away from this: tools are important, absolutely, but it's all about method. You have to be, most of you are probably from a science or engineering background, and you know that method is sort of what separates science from non-science. And it's all about method and sort of developing and refining your own method and technique. And of course, it's also about resources. How much time can you spend on tuning an application and so forth? But that's not the topic here. Okay, simple problem. Let's assume, to have something specific in mind, you would like to write multiple 2D array variables in some kind of a time sequenced fashion. And I put up a little picture up here. So we are looking at two-dimensional arrays, rows by columns. And for each time step, we are just looking at a certain number of them. And then in the parallel context, you can then think about sort of strong scaling versus weak scaling, which means that either you keep the size of that array constant, and then as you increase the number of processes, each process will write less and less data, which of course will not give you a tremendous speed up for very large numbers of processors. But then the weak scaling, which we will consider today, which is where you keep the per process I/O workload, so to speak, constant, and we will be writing more and more data as we add processes to it. And we just want to read and write them. And this example is actually not completely synthetic or artificial. If you go to the RDOS repository, and this is all hyperlinked here, there is an example program in there that does exactly that. And so the numbers, the parameters that you can keep in mind is we are doing, let's say, order of tens, in this case 20 time steps. We are looking at 500 such arrays in each time step or step. And the dimensions of these two-dimensional arrays are sort of 100 rows times 200 columns. And so I would submit that this is comprehensible, that is not totally artificial or synthetic. There are many practical applications that you can, I think everybody can think about where this is the problem to be solved. And you might think, well, since this is so simple, what could possibly go wrong? Well, the first thing is, if you take a step back, there is actually quite a bit of missing information here, because we talked about it as like in memory situation, this is what I have in memory in some form, in arrays or something like that. But we want to write that to an HDF5 file. And we have to then think about, well, how do we lay this out? How do we represent all that in HDF5? And there are quite a few choices there. Number one is, yes, these individual two-dimensional arrays might be two-dimensional in memory or somehow, but that doesn't mean we have to necessarily represent them like that in the HDF5 file. So the first thing we can think about is we could represent them kind of verbatim source to destination as two-dimensional array variables or data sets, as we call them in HDF5. We could stack them together in a three-dimensional array, or we could even go one up and pack all that into a four-dimensional data set. And I'm at this point just talking about it logically. We then have to think about, well, are they really fixed size and whatnot? But that's a whole other story, just logically. Are the extents known a priori? In some cases they are, in many cases they aren't. Then it's a question of how are these dimensions ordered? So the problem formulation kind of suggested that this is sort of time-driven, but it could also be the other way around. It could be that for each variable you record sort of a two-dimensional bundle of time series, so to speak. So the question is, how are these dimensions ordered? And in a framework like HDF5, we have additional capabilities of structuring information with groups, for example. So we could have a group for each time step or a group for multiple arrays. That's a consideration. Another consideration is, okay, once we've settled on a way how the data is written, the question is, since we are interested in read and write performance, is the data really read back the same way, or is it written one way and read back in another way, and then where's the sweet spot if there is one? And then finally, we have to put bytes on disk somehow, or into a file system, into a file, or multiple files. What's the storage layout? And finally, what's the file system or data store that we are actually targeting? Of course, in an HPC environment, that would be some kind of parallel file system. But then when we talk about things like MPI-IO, we can think about different modes, collective, independent. I haven't even talked about, as most of you know, there are different versions of HDF5, different release versions of the software. That might be another dimension. So there are just lots of variables to think about. Now, there is a little bit of a dilemma here. And I would describe this dilemma sort of as the raw HDF5 dilemma. What you want, and think about the problem formulation, writing these two-dimensional arrays. Let's say you are in Python in H5Py, you have NumPy arrays and so forth, then of course H5Py takes care of a lot of things for you. You will just work with NumPy arrays or data frames or something like that. And in the end, there will be an HDF5 file. You don't have to think about layout. Things have been decided, have been programmed for you in the sense that, this sort of very simplistic remote control will have been mapped. The buttons of that will have been mapped somehow onto groups of buttons or buttons on this programmable, very comprehensive API called HDF5 that you choose when you include HDF5.h. Unfortunately, this is not the end of the story, because the regression continues from there as you add more complications like a parallel file system, other runtime layers and so forth. There's just more and more regression there. So there is a little bit of a dilemma here, but that's why it's important sort of to start simple and then at the right time, at least, to try to bring in the tools that tell you whether things are going according to plan or whether there are sort of forks in the road. Now, for this set of experiments that we will cover today, I chose sort of 3 problem dimensions, so to speak. Number 1 is to experiment with the griddings. So to think about, let's write to 2-dimensional data sets or to 3-dimensional or 4-dimensional data sets, and there are different combinations here. There are sort of 6 conceivable griddings. There are 2 layouts that we can consider here, contiguous or chunked. There are other options, but today we'll limit to this. And of course, in the case of contiguous, we would make the assumption that we have some a priori knowledge about sort of the extents of these dimensions. And there are cases when that's the case. There are other situations when that's not the case. So we would use chunked layout, fine. And then to get going a little bit in the parallel direction, look at collective or independent MPI IO modes. So 6 times 2 times 2 is 24. So that's one of the magic numbers to keep in mind throughout this discussion. For everything, there are 25 different ways how we can run it. Okay, 24. Now, as I said earlier, in part 2, we will look at sort of a real cluster environment. For this experiment, we are not going to make it too complicated. We will just use something that everybody has access to. And so what I did is I just took an instance that has 8 virtual CPUs, 32 gigabytes of RAM in the Google Cloud. Other fine choices are available. It's just running vanilla Ubuntu 20, and it has 2 NVMe attached SSDs, each about 375 gigabytes, and I just sort of use the Linux type soft RAID to create a RAID 0 volume, and that if you run FIO or your preferred IO benchmark test, you see that's actually a nice little system. You can, with 1 megabyte block size, you can write about 800 megabytes per second. And then if you drop the block size to 4 kilobytes, you still can read at about 1400 megabytes per second, and you can write at 600 megabytes per second. And the scripts in the GitHub repo, there is a gcloud subfolder. The scripts, how to create the RAID array and how to start the whole instance, they are all included. So if you would like to repeat this, it's all there. Now, if you look at the source code for this thing that I call HDF-IO test, the source code has actually a relatively simple structure. There's an ini file that describes the specific combination, meaning are we writing 2 or 3 or 4 dimensional arrays? What kind of IO do we do? do we, in terms of the dimension ordering, do we do time first and then array, and then the actual length or rows and columns, or do we do array, time, rows and columns? That's all specified in that ini file. And there's an ini file generator that generates all 24 combinations. So you have all those ini files. Then we sort of create the HDF5 file. There's a write phase during which we create the data sets. We close the HDF5 file, reopen it, read it back, close the HDF5 file, and then we write a CSV output file with the timings where we measure how much time does it take to create the data sets, how much time does it take to write these data sets, and how much time does it take to read. And that's it. And it's CSV because then you can easily concatenate all of them, put them in a spreadsheet, and produce some hopefully interesting graphs. Okay, so baseline, remember 24 combinations. We are only interested for part 1 in weak scaling. And just a quick back of the envelope calculation, we are doing 20 steps. And in each step, we are writing 500 arrays. Each of them is 100 by 200 times double precision. So we are writing about 80 megabytes per process per step. And we are looking at single processor performance, and then we just take a simple 4-processor grid or process grid, 1 by 4, 1 process row, 4 process columns, 2 by 2 or 4 by 1. And as I said, these are the times that we measure. Okay, if we do that, we take all the HDF5 library defaults, we get something that looks a little bit overwhelming, and I'll explain it. So first of all, there are 24 bars. 24 combinations, there are 24 bars. And I want you to initially focus sort of on this upper left-hand corner, which acts like a legend. That's actually the single processor run. So here I indicate the format of the process grid. 1 by 1 is just a single processor. Now, in terms of the bar height you can read as wall time in the sense that it's in seconds, and it has 3 components. We measure creation time, write time, and read time, color-coded. Yellow is reading, red is writing, and blue is creating. And so that means that if a bar is taller, we spend more time, which is bad for performance from a performance perspective, and a shorter bar is good because we spend less time. So for example, this bar here, you guys can see my mouse, right? No? Okay, good. Right, so this bar here is probably the shortest in that collection. That would be the best performance because the program runs quickest. Now, as I said, among this 24 different ways how we can run this, we group them into sort of 3 blocks of 8 by the dimensions. So the first 8 bars correspond to where we write to 2-dimensional arrays. The next 8 bars correspond to writing to 3-dimensional arrays. And the last 8 correspond to writing to a 4-dimensional array. And then within this block structure, there is sort of a sub-block structure where the first 4 bars correspond to contiguously laid out arrays in the file, and the next 4 bars correspond to a chunked layout in the file. And so if you just look at this, unfortunately, there seems to be a lot of variability because conceptually, logically, we are doing the same thing. All these bars do exactly the same thing unless there's a bug in the program, but let's assume that that's not the case for now. There's a lot of variability. Ideally, it would be the case that the performance would be nearly identical, and then we could say, it doesn't really matter whether we write to 2-dimensional or 3-dimensional or 4-dimensional arrays, or whether it's chunked or contiguous, it doesn't matter. The performance is more or less the same. That does not appear to be the case. Now, so this is the legend. I hope that's clear. And sort of the remaining 3 entries correspond to parallel runs. So in this case, it would be a 1x4 process topology, 4x1 and 2x2. What I would also point out, and I don't want to mislead anybody here, the scaling is slightly different for these different graphs, which again highlights that the performance is quite different. So here it goes up to 3 seconds, here it goes up to 15 seconds, here it's about 12, and the same here with 12. So there's quite a bit of variability. And so a few observations. Number one, as I said already, there's a 3 to 4x variability in performance, which is not good, or which is we have to deal with somehow. There appears to be data set creation overhead because, again, as a reminder, blue represents time that we are spending creating data sets. And yeah, for all these bars where there is a substantial blue portion, we are not purely spending time reading and writing data. We are doing other stuff that has nothing to do with reading and writing data, and that will, of course, reduce perceived performance. It also appears, given the ordering that we have, is that that seems to be most pronounced for when we use chunking. So as I said, for each of these sub-blocks, the upper 4 bars correspond to chunked layout. That's where the creation overhead appears to be the most pronounced. And if you know a little bit about HDF5, that makes sense to a degree. But then on the other hand, do we really have to live with that, or is there something we can do about it? Process topology appears to matter, although since these are just timings, I wouldn't read too much into that. But just the fact that the range is sort of different for different topologies, and the variability is also different. Process topology seems to matter in some form. But then, of course, we will very quickly find that just 3 timings, of course, you have to be careful to read too much into that. So it tells us something. Maybe the loudest and clearest is this creation overhead. But otherwise, I would not read too much into these results. Okay, but this creation overhead seems to be a factor, and so let's quickly see what we can do about that. Now, if you ask yourself, well, what does data set creation really mean? Then it means 3 things. It means you have to allocate storage, and then there's a question, when does that happen? You have to initialize the data set. Well, you have to see if you want to initialize it at all, and then when and to what value. And then there is a little bit of a metadata management portion, which we won't worry about. And the library has certain defaults because we haven't really said anything to the contrary, and they may not be what you expect. And there are functions in the HDF5 library that allow you to take control of some of these aspects. And if you read up in the documentation and think about our original problem formulation, well, in this particular case, we are really overriding everything. And there's really no need for initialization. It's like the difference between malloc and calloc. Do we really care about that piece of memory that we are asking for is zeroed out? Not in this case. So if we want to suggest to HDF5 that we don't care about that initialization, we can do that by calling h5p set fill time and set it to never, and then we don't incur what actually turns out to be a write. Ultimately, the initialization of these elements in the file is a write operation. So if we do that, again, the sort of the legend and the layout is exactly the same. What we achieve is we can pretty much take away the blue, and then everything kind of collapses down, and also the ranges change. And yeah, sort of it was a low-hanging fruit, and for people who know this a little bit, a pretty obvious thing to do, and it has an effect. And good news. But there is still, maybe apart from this 4x1 case, but again, I wouldn't pinpoint that to a particular shape of topology where the variability is relatively low. It's sort of around 4 seconds here, but otherwise not too tremendous a variability. There's still a huge variability in the other two cases. So then the question would be, well, where do we go from here? Unfortunately, we've kind of run out of information in the sense that, yeah, we have these timings, but then that doesn't really tell us very much to make progress from here. And so the next steps would be, we want to bring in some tools, and we will talk about that next. And in part 2, we will talk about, again, this was running against the RAID 0 volume with SSDs, everything local. We don't have to worry too much about interconnects and things like that. Really bringing in tools to bring in additional information that helps us either understand that there's nothing we can do, or potentially opens up new lines of improvement. And the 3 tools that we will be looking at are the formerly called Google Performance Tools, Darshan, and Recorder. Okay, so and again, there is a shell script included in the Google Cloud folder that shows you how to run performance tools to create some of these traces, and then you can open up these traces in K-cache grind, and this is what you see. So I've just taken 2 samples here, run number 8 and run number 17, and even without going into details, you can see already there are different things going on here. Because if I tell you that this is the call graph inferred from the sampling, and this is the call graph inferred from the sampling for run 8, well, just topologically, they look different. There are different things going on here. So, and then of course, this is a tool that lets you look into carefully where are you spending your time. And this is actually very important. Ultimately, of course, we want parallel, and we want HPC, and we want all of that. But let's not do the second step before the first, which is sort of carefully looking at even just to confirm that everything is in order, it's good to look at single process performance. I mean, it's happened to me many times, and maybe to some of you as well, is that you were surprised when you looked at the single process sort of profile breakdown, you didn't expect that you spend time the way you spend, or your application spent your time. And so this is the first tool, very helpful. And it also, if you try to better understand what is really happening in the HDF5 library, should you want to go down that path, that tells you something. Number 1. The next tool that is very helpful in this context is Darshan. It's developed by the guys up in Argonne. It's available on GitLab, and I would encourage you to really use the latest version. If you have an installation on the system that you use, and there's an older version of Darshan, that's okay. I would probably still encourage you to just download the source code and build your own version, because there are, as far as HDF5 support goes, and then also the Python module that's available now in the latest version of Darshan. I think those are 2 critical things that are definitely worth building your own investment, or asking your administrator to put in place the latest version. It gives you performance counters for POSIX, MPI-IO, HDF5, and it organizes them sort of as streams of events or performance counters that are tagged by record IDs, and they are sort of separate record IDs for individual files. And if you build it with the HDF support for HDF5 datasets and files, and then you get performance counters like how many reads that occur in my application of a size between 1K and 10K, how often did POSIX switch between read and writes, or in the case of the HDF5 module, how many of these regular hyperslab selections did I do? And out of the box, you get tools for parsing these Darshan files and summarization. So the diagram that's taken from the Darshan website, this is the kind of summary information that you get. But as these things go with the performance counters, you will have some expectations of your own, which performance counters you think will tell you something about your application. And then I highly recommend to use that Python module to really pull it out, put it into something like a pandas data frame, and then use matplotlib to create your own visualization. And I included, thanks to my colleague Alexander Jelinek, who sort of was a pioneer in playing and exploring this tool, customize that visualization to really bring out the information that you need. And here's an example. I took the 4x1 process topology run 7, and I just chose that randomly. They all look interesting, and next time we do a more careful analysis, but this is just to show you a real example, what you will see in practice. And I'm just going to focus on the sort of lower right-hand corner here. Is what this diagram shows us is basically how many I/O operations, in this case, reads and writes, purple are reads, green are writes, how many of these I/O operations did we do? And on the x-axis, how big was the underlying I/O range, so to speak? So between 100K and 1 megabyte, and then sort of these smaller brackets. And I circled sort of 2 areas that show us that there's trouble here. By the way, this is the run 7 without the optimization to not initialize these chunks. But it's actually interesting, and this is where bringing in other tools is helpful. You want, if ever possible, you would like independent confirmation when from one set of results you made a conclusion. It is nice that if you have an independent tool to get some kind of confirmation that your previous conclusion is actually sound, because now you have a second way to confirm that. Because if you look at that orange, that right-hand ellipses, what that tells us is basically we did 40,000 read operations of some size between 100K and 1 megabyte, but we did twice as many write operations. Well, why would that be? In our problem formulation, the reads and writes should be symmetric. So how can that be? And yes, indeed, since we have not done in this particular run the optimization for not to initialize the chunks, they get written twice. So that's why we have twice as many writes as read. And there must be 40,000 because we have 4 MPI processes and we have 20 time steps of 500 arrays. So that's 4 times 10,000. So 40,000 makes sense. But yeah, that discrepancy that we have twice as many writes as reads, that's one way to explain that. And then the red ellipse I'm not going to talk about, but this is another indication of that there's trouble, because this is just, especially in when we think ahead that we want to run this on a parallel file system, we are doing large numbers up to 100,000 or beyond 100,000 of tiny reads and writes, and that can't be good. But this is another way. This is the kind of information Darshan gives you, and if you, once you get the hang of it, how to read it, and it's well worth your time, spending time to understand how to read this information. It gives you clues of where your next sort of improvement target might be. I'm not going to spend much time on this. We had a summer intern who did some interesting research about creating additional sort of characterization of applications, of multiple applications. But in this case, we said we do 24 combinations, 24 runs of each. You can view that as 24 different applications or variants of the same application. It doesn't really matter. But he found a way that you can actually correlate these different Darshan performance counters and then in a way assess, well, how similar or dissimilar are these runs. And he has a poster at SC20, and if you're interested, I encourage you to look at this. The only thing I would point out is, again, here's our magic number 24 again. So we have 24 different combinations. And since the similarity is symmetric, this correlation matrix, so to speak, must be symmetric. One or red means very similar or identical almost. Purple means very dissimilar or very uncorrelated. And so this is a symmetric matrix. We have ones on the diagonal, things correlated with themselves or just one. But you see here already that block structure. Remember that block structure comes from 2-dimensional arrays, 3-dimensional arrays, 4-dimensional arrays. And what we see here is these diagonal blocks. They sort of correlate 2-dimensional runs with 2-dimensional runs in the center block, 3-dimensional runs with 3-dimensional runs, and then 4-dimensional runs with 4-dimensional runs. So they among themselves are more similar than compared to, for example, this block here correlates 4-dimensional with 3-dimensional or 4-dimensional with 2-dimensional. And that just tells us things, yeah, drift sort of farther apart and behave very differently. Interesting work. No time to, not much time to spend on that here today. The third tool, and again, we had a phenomenal summer intern here at the HDF group, developed this tool called Recorder. And this picture is taken from his GitHub page that you should check out. It sort of builds, it gives you more information in a way than Darshan. It also gives you information sort of broken up by what he calls multi-level, HDF5, MPI-IO POSIX, but it adds sort of the timing. You can break it out by timing and by rank, so it gives you time series if you wish. And it gives you function statistics, counts, timings, per rank access patterns, accessed offsets by rank and by time. And he also tries to detect, for example, data hazards like read after write dependencies, write after read, write after write, and so forth. And it also has some nice onboard report generation capabilities where these figures are being generated. And what happens when you apply a Recorder to our problem? Well, I've just, again, taken a few samples, 7, 17, 14, and 24. You see things that make sense, but then things that don't make sense. So on the vertical axis, the y-axis is the offset in the file at which you read or write. And the horizontal dimension, the x-axis, is time. So what we like to see is what's sort of in the upper two pictures, which is, yeah, in increasing order, we are sort of writing at ever greater offsets, and then we read sort of, we read the same information sort of back. Maybe since it's being read faster, the angle of this line is steeper. But then we also see some disturbing things, and that's again why I put the trouble here, although I will get into describing in detail what's going on here at the next time, is I zoomed actually in. So the nice thing of some of the reports that Chen Wang's tool creates is you get an HTML page with all these diagrams, but then you have controls where you can sort of pan and zoom and so forth, so you can look at the fine structure of some of these things. So what appears to be happening here is if I zoom in just on the right portion of it, we have these fine, we seem to be writing, but we seem to be covering the same the same offsets over and over again. Now, in this case, it's an artifact because if you zoom in deeper, you actually would see that they are sort of isolated little strides that don't really perfectly overlap like this. So that's an artifact of the visualization. But then over here, it's much, much clearer. There's something going on. We seem to be writing, and this would be the initialization portion for the chunks. But then what's going on over here? What is happening there? And yeah, we'll talk about that next time. But recorder it's easy to use. It gives you a lot of information. Download and use it. And it's when you use the Google Cloud instance, there's a script in there that will just install it, and there's a run script that shows you how to run it. Now, summary for today. You should know what your system's capabilities are, because otherwise it's easy to get off on the wrong foot. So when it comes to just simple things, just measure. For 1 megabyte blocks, how fast can I write? 4 kilobyte blocks, how fast can I read and write, just to not get off on the wrong foot there. It's also important to find a quiet corner. Unfortunately, many systems, you get access to them, great, but there's just so much activity, so much noise there that, again, it's easy to get off on the wrong foot unless you run it tens or dozens or many, many more times to sort of get the variance, the variability down. And cloud environments are just, at least for single process and small numbers of processes environments, are a great way to get started. It's also important to do back of the envelope calculations. So remember in the Darshan case, for example, well, you know, I'm doing 40,000 reads and writes, and sort of those types of numbers, how big are the writes that you are doing? All of these things you want to have together on a small cheat sheet, so that when you look at interpreting the output from the tools, that you don't get lost there. It helps you to really spot bugs and potential trouble spots. It's also important to keep the number of turtles or variables as small as possible. So like in this exercise, sure, you can, if you have a parallel file system, you can set that up in the cloud as well. It doesn't help. In the first round of analysis, it doesn't help. It's just additional things that can go wrong and that will go wrong under the right circumstances. So keep the number of variables small. Definitely start with a single process analysis. You can save yourself a lot of time by doing a single process analysis first. You may discover things that you didn't know or that the developer didn't tell you that this code does, before you sort of go off on a wild goose chase and come up with complicated explanations for things that are actually maybe straightforward. Using the right tools for the job. You really, user-based instrumentation is great. Somebody might have done a good job giving you all these timings and so forth, but you have to understand when you have exhausted that information and when it's time to really bring in the right kind of tool to give you that additional information. But you also want to do that step by step. Too much information, sort of the fire hose, can be equally confusing as too little information where you think you can just get by putting a few more printfs and so forth in there. That is typically not a good idea. Next time we will do an in-depth analysis of the Darshan results and the recorder plots, and really move into sort of MPI-IO and parallel file system, and then also look at that question of what can be done for strong scaling. Okay, I think that's 45 minutes.
Thank you very much, Gerd. I wanted to jump in and mention real quick, so we're getting ready to enter the Q&A period. If you would like, you can unmute to talk or put it in the chat. We do already have a question there in the chat, Gerd, if you want to take a look.
Okay.
But I did want to let everyone know we'll be having a HDF users group meeting, a virtual event, of course, this year, October 13th through 16th. that'll start off on the 13th with a hands-on tutorial, HDF tutorial presented by Gerd and Stephen Varga. We'd love to have you join us, so please register. And I've put the link to register on the chat. And of course, I've been sending emails and putting it on the forum. So there's the link. We'd love to have you there. And I'll go ahead and turn it back to Gerd for the question and answer period.
Thank you. Yes, so the first question I'm reading here is, can users extend the Darshan instrumentation with an HDF5? Sort of as, from a technical point of view, I would say it's open source. Yes, absolutely. No, but I would ask the guys up at Argonne. So in principle, I would say yes, and they might be very open to the idea of extending it. The coverage is actually pretty good. So if you look at the H5D and H5, so at the moment it covers quite a few H5D and H5F calls. So at the moment there's no support for attributes and no support for types. So if you have specific things in mind, I think you can try yourself. I personally have not tried to extend it myself. So yeah, that's what I would say. I mean, these guys are very open. I would just approach them. If you have a specific type of module or counter in mind, see what their recommendation is. If they might just say, oh yeah, just include that header file and declare a new counter and implement these aggregation functions. Or they might say, oh yeah, we are working on that already and it's coming in the next release. That would be my response. And then a version of Darshan Instruments, it's still in a branch, Suren. I think I beg to differ. I think in H5, in Darshan 3.2.1, it includes the HDF5 module. It's not built by default, so you have to specify. I forgot in the configure file, but if you look in the scripts in the G-Cloud folder, I have the configuration options in there. I think it's like -- module HDF5, and then you have to specify the installation path of your, and then it gets compiled, the HDF5 module gets compiled. And I should have mentioned, yeah, if you use PNet CDF or some of the other runtime, or RDOS, for example, does it support RDOS? I'm actually not sure off the top of my head. But you can compile these additional modules into Darshan, or I think there are some Luster specific counters and so forth. So I think it's there in Darshan 3.2.1. HDF support is there. You just have to enable it when you build it. The Python module, however, go ahead. Sorry,
this is Suren here. So yeah, I think we are working with Darshan folks as part of the ECP project to include profiling HDF5 calls, including all the HDF5 attribute calls, related calls, and IO calls. So I think the link that I mentioned has the latest development branch, has all those details. So that's what I was answering a previous question. So.
Okay, good. Thank you. Thanks for that clarification. Yeah. So it's even better news. Any other questions? I actually can't see how. Oh, we have 54 participants. Okay, wow, that's quite a turnout. Yeah.
Gerd?
Yes?
Gerd, it's Steve. I don't have any questions.
Steve's one of our most brilliant coworkers. I think he's, business development and HR at the office. So just to wrap up, and anyone feel free to jump in if you do have a question. And we're always willing to talk to you on the forum.hdfgroup.org. And you'll get a lot of employees as well as community members there to help you. So I will work on cleaning up this video recording, and I have Gerd's slides, and the link to the GitHub repo was posted earlier, but I will also post that on the forum. So you'll be able to find all the related material there. And if you have questions that come up later, feel free to ask them there. I believe that's it then.
Okay, thank you.
All right. Thank you, everyone. Have a good day.
Thanks. Bye.